This is a video walkthrough for practice 4A on basic exponent rules. Our first question is a think about it. If A is a whole number that is 2 or greater, why does raising it to a negative exponent give a fractional result? Well, let's think about what happens when we raise a number to a negative exponent. That re-expresses it as 1 divided by a to the second power. What's going to happen is we're going to divide 1 by a number that is greater than 1, and so that result is going to be a fractional result. Another way to express this is if positive exponents represent repeated multiplication, then negative exponents represent repeated division. When we divide by a whole number that is larger than 1, so I'll just write greater than 1, the result is a fraction. What I mean by that is a proper fraction, a number between 0 and 1. All right, let's take a look at 2 through 30. We're going to follow our order of operations for each of these numeric expressions. So we have 3 minus 11 times, and 6 to the negative 1 power is 1/6. Now let's perform the multiplication. 11 times 1/6 is 11/6. And in order to subtract, we need a common denominator. 3 is the same as 18/6. 18/6 minus 11/6 is 7/6, and that's our final result. You don't need to change an improper fraction to a mixed number. Improper fractions are just fine and actually preferable in algebra. In number 3, we have exponents to evaluate first. So 1/5 plus 1 over 2 cubed, and 2 cubed is 8. So now 1/5 plus 1/8. Our common denominator will be 40. So that's 8/40 plus 5/40, and the result is 13/40. For number 4, we can use the addition of exponents. Whenever we multiply like bases together, we add the exponents. Don't forget there is an exponent understood of 1 on that factor of 5. So this gives us 5 to the negative 2 plus 3 plus 1, which is 5 to the 2 power, and that's going to give us a result of 25. Notice we don't have to evaluate all the individual expressions. We can just multiply together and add the exponents because we're multiplying like bases together. For number 5, 1 divided by 3 to the negative 4 is the same as 3 to the positive 4. We can move that factor from the numerator to the denominator to the numerator and change the sign of its exponent. 3 to the positive 4 is 81. Another possible way to evaluate this one is to rewrite it as 1 divided by 1/81st, which is 1 divided by 1/81st, written with a different division symbol. And we know how to divide fractions. Simply multiply by the reciprocal, and that'll give us a result of 81 as well. So there are 2 ways to evaluate that expression. For number 16, the easiest way to evaluate this one is to subtract the exponents. So we have 14 to the 17 minus 19, which is 14 to the negative 2, and that's 1 over 14 squared, or 1 divided by 14 squared, which is 1/196th. Remember, 14 squared is one of the numbers on your perfect square memory list. For number 7, 7 to the 102 divided by 7 to the 99 is 7 to the 102 minus 99 power, which is 7 cubed. That's another number on your perfect cube memory list, 343. Number 8, 2 to the 3 divided by 2 to the negative 1. Since the bases are like, we keep the base and subtract the exponents. 3 minus negative 1 is 4, and 2 raised to the 4th power is 16. For number 9, the bases are the same. We're dividing, so we can subtract exponents. Negative 7 minus negative 6. Negative 7 minus negative 6 is negative 1, so now we have 8 to the negative 1, which is 1/8. For number 10, the bases are like again, so we'll keep the base and add the exponents. 3 plus negative 5 plus 6 is 4, so final result is n to the 4th power. In number 11, we have multiplication that's implied right there between the 7 and the k, and k is being raised to the negative 1 power. Exponents must be performed first, so k to the negative 1 power is 1 divided by k, and then 7 times 1 over k is 7 over k. In number 12, we have parentheses. That means that the exponent applies to everything in the parentheses. So 7k to the negative 1 is 1 over 7k to the positive 1. Of course, 7k to the positive 1 is just 7k, so 1 over 7k. Notice the difference in these two results. Notice where the exponent in number 11 only applied to the k, and so the k moved from the numerator to the denominator. And then in number 12, the exponent applied to the entire parentheses, so the entire parentheses moved from the numerator to the denominator in number 12. For number 13, we are dividing like bases, so you may subtract the exponents. 5 minus negative 4 is 9. So y to the 9th is the final result. Notice in number 14 that you do not have like bases. So, since we have factors in the numerator that have negative exponents and factors in the denominator that have negative exponents, we can simply move the factors. So x to the negative 7 in the numerator becomes a factor of x to the positive 7 in the denominator in a result, and y to the negative 2 in the denominator becomes a factor of y to the positive 2 in the numerator in that result. We can work this one a different way if you wish. X to the negative 7 is 1 divided by x to the 7th. Y to the negative 2 is 1 divided by y to the 2, and re-expressed using a different division symbol. That's 1 over x squared divided by 1 over y squared. And when we divide fractions, we multiply by the reciprocal. So that gives us a result of y squared over x to the 7th. Same result, different technique. Number 15, we have some 0 powers there. 3 raised to the 0 power is 1. And then t raised to the 0 power is 1. Now we can perform the multiplication. 3 times 1 is 1, and that result gives us negative 2. For number 16, the exponent applies to the x, so x to the negative 2 is 1 divided by x squared. 5 times 1 divided by x squared is 5 divided by x squared. For number 17, negative 7 times w to the 4th times 20 times w to the 9th. This is all multiplication, so may be performed in any order. Negative 7 times 20 is negative 140. W to the 4th times w to the 9th is w to the 4 plus 9, which is w to the 13th. That's as much simplification as we can do. Number 18, we have an exponential expression to simplify. 2 to the negative 4 is 1 divided by 2 to the 4th power, or 1/16, times x is x divided by 16, or x over 16. For number 19, when a power is raised to a power, you multiply the two exponents. 5 times 7 is 35, so that's k to the 35th power. And in number 20, we have a bunch of powers of x. The multiplication in the numerator, we can add those exponents together. Negative 5 plus 4 is negative 5. And then let's bring over the denominator. And if you wish, you can switch the location of each of those factors. the factor of x to the negative 3 can move to the numerator and become an x to the positive 3. The factor of x to the negative 5 can move to the denominator, become a factor of x to the 5. And then 3 minus 5 is negative 2, so that's an x to the negative 2, 1 over x squared. Do notice that you could have simply subtracted in the first step. X to the negative 5 divided by x to the negative 3 could have been x to the negative 5 minus negative 3, which would also give us an x to the negative 2. Remember, that has to be expressed as a positive exponent, so that's 1 divided by x to the 2. For number 21, power to a power, multiply the exponents, and a negative times a positive is a negative. That must be expressed using positive exponents, so that's 1 divided by u to the 8th. In 22, again a power to a power. However, this time a negative times a negative is a positive, so y to the positive 24 is the result. For number 23, we have an exponential expression here. 2x to the 4th raised to the 3rd power really means 2x to the 4th times 2x to the 4th times 2x to the 4th. And that'll bring down that x to the 5th. Now this is all multiplication. 2 times 2 times 2 is 8. And all of the exponential expressions involving x have the same base, so we'll keep the base and add the exponents. 4 plus 4 plus 4 plus 5 is 17, so 8x to the 17th. For number 24, in the numerator we have a power to a power, so multiply the exponents, that's c to the negative 28, divided by c to the negative 2. Now we can subtract the exponents, and that gives us c to the negative 26th power, which is 1 divided by c to the 26th power. In number 25, we can evaluate that exponential expression first. Power to a power, exponents get multiplied, that's y to the 15th times y to the negative 1. Now add the exponents and keep the same base, that's y to the 14th power. For number 26, we have multiple factors here, so what I'm going to do is I'm going to change the location of any factors that have negative exponents. So I'm going to leave that factor of a to the positive 1 in the denominator, but move all the other factors. The a to the negative 2 in the numerator can move to the denominator and become a factor of a to the positive 2. The b to the negative 3 in the numerator can move to the denominator to become a factor of b to the positive 3. And b to the negative 5 can become a b to the 5 in the numerator. And now we can cancel common factors. That'll leave us with a b squared in the numerator and an a cubed in the denominator. For number 27, power to a power, multiply the exponents, that's w to the negative 28 times w to the 10. And now that we're multiplying like bases together, keep the base and add the exponents, that's w to the negative 18, which is 1 divided by w to the 18th power. In number 28, again a power to a power, so multiply those exponents, m to the 10th times m to the negative 3. Like bases, multiplying, add the exponents, that's m to the 7th power. For number 29, we can again move any factors that are negative exponentiated. So that moves the factor of 9 to the negative 3 to the numerator, 9 to the positive 3, 9 to the negative 5 in the numerator, moves to the denominator, becomes a factor of 9 to the positive 5. a to the 4th has a positive exponent, can stay where it is. And then a to the negative 1 is going to move to the numerator, become a positive 1 exponent. Now we can cancel common factors. That's going to leave us with a 9 squared downstairs and an a to the 5th upstairs. Simplifying the numeric expression, that's a to the 5th divided by 81. For number 30, 14 divided by 2, cancel common factors, that's 7. So now we have 7 x to the negative 2 y z to the negative 4 divided by x y z. So I'm going to take any factors that have negative exponents, and I'm going to move their location. So x times x squared, and y, and z times z to the fourth. Our common factors of y can cancel, and that's just going to leave this expression as 7 divided by x cubed times z raised to the 5th power. In 31 through 36, we are solving equations. What we'll need to remember here is that if a base raised to a equals the same base raised to the b power, then a and b, the exponents, must be equal. So for number 31, 13 to the 2x minus 1 equals 13 to the 14 minus x. 2x minus 1 must be equal to 14 minus x. Adding x to both sides and adding 1, we get 3x equals 15 and x is equal to 5. For number 32, we need to consolidate each of these sides of the equation by using properties of exponents. 5 to the 3x times 5 to the 2nd power is 5 to the 3x plus 2, because when we multiply like bases, we add the exponents. And then on the right side, 5 to the 2x plus 9. Now that we have the same base, the two exponents must be equal. 3x plus 2 is equal to 2x plus 9. That gives us x plus 2 is equal to 9, and x is 7. For number 33, there is a factor of 3 that has an understood exponent of 1. When we divide, we subtract exponents, so that is 3 to the 5x minus 1. And when we multiply, we add the exponents, so the exponent on the right is 3x plus 7. So 5x minus 1 must be equal to 3x plus 7. Subtract 3x, add 1, and that gives us a result of x is equal to positive 4. For number 34, we have a power to a power. Power to a power, the exponents get multiplied. And when we multiply like bases together, we add the exponents. So now we can equate the exponents. For x is equal to x plus 6. Subtracting x and dividing by 3, x must be 2. For 35, power to a power, that's 6 to the 5x. And we have more simplification on the left side to do. When we multiply, we add the exponents together. So that gives us 6 to the 5x minus 2 equals 6 to the 8x plus 7. So the two exponents must be equal to one another. Subtracting 5x from both sides, and then subtracting 7. That's going to give us a result of x is equal to negative 3. And for 36, we have more properties of exponents to use. Power to a power, multiply those exponents. And same on the right, multiply the exponents. Let's understand that that 2 on the right side has an understood exponent of 1. Now, 2 to the 5x minus 7 is equal to 2 to the 3x plus 1. Because when we divide, we subtract exponents. When we multiply, we add the exponents. So now 5x minus 7 must be equal to 3x plus 1. And that gives us 2x is equal to 8 and x is equal to 4. For the last part of the homework, f of x equals 7 times x squared. We want to find f of the opposite of x. So if x got replaced with the opposite of x, then the x on the right side of the equation must also get replaced with the opposite of x. The opposite of x times itself is x squared, because a negative times a negative is a positive. For number 38, f of x to the 6th, is 7 times x to the 6th squared. So that's 7 times x to the 12th power. For number 39, f of 3x to the 5th is 7 times 3x to the 5th squared. And let's remember that that means 3x to the 5th times 3x to the 5th. That's all multiplication. 3 times 3 is 9, times 7 is 63. X to the 5th times x to the 5th is x to the 10th, because when we multiply, we add the exponents together if the bases are alike. And for number 40, f of x minus 10 is 7 times x minus 10 squared. Remember, there is no distributive property for exponents over subtraction, so this has to be treated as x minus 10 times x minus 10. And it might be easiest to multiply these two factors together first, although you can multiply in any order. Foiling x squared minus 10x plus 100, or 7 times x squared minus 20x plus 100, and then multiplying by 7, 7x squared minus 140x plus 700 is what the expression f of x minus 10 is simplified to.